All right, the first section of Chapter 7. It's exponential functions and their graphs. This whole Chapter 7 should be a review from Algebra 2 and Pre-Calculus, where we talk in depth about exponential functions. We'll talk about logarithmic functions. And then Chapter 8, super short, where we talk about how we apply them to calculus. It's a very short Chapter 8. So we should be able to get through these two chapters fairly easily. Chapter 8 is short because it's mostly just formulas. You use the formulas to apply it to finding a derivative and integrating, like we've been doing a lot of in the past few chapters. But Chapter 7 is all review. Okay, so let's get started. First, it's probably good that we define what an exponential function is. Definition of an exponential function. The exponential function f with base a is denoted by f of x equals a to the power of x. A few things we need to note. A can't be 1. Why? Because if it's 1, it's just going to be 1 the whole time no matter what my input is. Okay? If it was 1 to the power of x, no matter what x is, the output's going to be 1. So that's silly. A must be greater than 0. And also x is any real number. Okay, any number you can put in there, that'll work. Alright, so we have two basic graphs, y equals a to the power of x and y equals a to the power of negative x. As you can see, with it being, when x is positive, as x increases, y increases, with the exponent being negative, as x increases, y decreases. A few things we should note. I want to talk about what the domain range of all these is. So domain, for both of them, I'm just going to write it once. For both of them, it's negative infinity to infinity. X, and you can put any real number in for x, and it will work. What's the range? The range is from 0 to infinity for both of them. Okay? Why? It can't ever be less than 0. Never. Okay? Because if you have a negative exponent, remember, you're just going to have a fraction. Okay? That's it. Okay? If it's positive, it's going to be really big. Okay? But if that exponent's negative, it's a fraction. So it can never be negative. It can be a fraction that's positive or a big number. Or bigger number, I should say. So that's your range. Y-intercept, as I labeled for both of them, y-intercept is at 0, 1. There is no x-intercept because it never crosses the x-axis. So there's no x-intercept, just a y-intercept. And for the original exponential function, it's 0, 1. Also, when's it increasing? For this graph, this is where it gets different. This is increasing the whole time. It's increasing the whole time. For y equals a to the power of x. For a to the power of negative x, it's decreasing the whole time, which is fair. And then, do we have a horizontal asymptote? HA? Yes, we do. The same one for both of them. Y equals 0. Okay? Y equals 0 is horizontal asymptote. It's never going to touch it. And just for fun, these are both continuous functions. There's no points of discontinuity. I'm not thrilled with how your book goes about talking about transformations, and also just to point out, in years past I usually make this my b value, this my a value. That's totally normal, but I chose, since your book makes this a value your base, just to be consistent with what I might ask you on homework and when we practice together, I made this the base, okay? So just a little note. So, some transformations. If b is negative, meaning that term in front of your base and exponent is negative, then it reflects over the x-axis. Reflects over x-axis. X has negative up front, meaning, as we noticed with the examples I showed you in the last slide, this negative reflects over the y. Reflects over y-axis. And then, of course, as you might be aware, I didn't mean to move it like that. Fix that. Yeah, more space now. Cool. So H is move left, right. K, shift up and down. Okay, so those are transformations you will be asked that, just like transformations did with polynomials and various other functions we've done in the past. Same story. So here's an exponential function. Now, this portion's natural base e, or base e. I want to talk about where that number comes from, because e is a number, even though it's a letter. It is a number, actually. And I want to talk about what that number is. So we have this exponential function right here, which you might have seen in various forms of examples you've seen over the years. Now, as x gets bigger and bigger, let's say x is 1, right? 1 over 1 is 1, 1 plus 1 is 2, 2 to the first power is 2, 2 to the power 1 is 2. And then as x keeps getting bigger and bigger, it slowly increases, okay, into what becomes this number that is approximately, I can keep going for on and on here, 2.71828, blah, 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 blah. And that number is known as base e, okay? That is what we would call, if a function is always continuous or moving, we would use base e. Okay? For example, you might say that population, for example, is it's always increasing or decreasing depending on where you're living, right? When it comes to a population of a city or a state or whatever, you're not going to just plop 1,000 people once a month or every day, right? For that matter, they're always going to be increasing continuously, right? They might come at one time or another time, or they might be leaving a city or state at one time or another. So that's an example where we might use base e for an exponential function, because it's always going to be increasing at every moment or decreasing depending on what's happening. Let's sketch the graph of one of these, shall we? Okay, so let's say we have f of x equals, let's say we have 3 base e to the power of 0.5x. Okay? Whenever we're doing any exponential function, not just base e, it's always best to start with what is our y-intercept, okay? Why is that important? Well, we know we have one, right? We won't have an x-intercept unless we have a shift up or down on the outside here, but we don't in this case. So we have no x-intercept, just a y-intercept. How do we know we have y-intercept? Because we can put 0 in for x, and an output will come as a result. So we put 0 in for x, e to the 0 power is 1, 1 times 3 is 3. So we have 0, 3 as your y-intercept. Now what's happening beyond here? Well, as we talked about before, this is positive, right? There's no negative. Since this is positive, that means it's going to be, as x increases, then the output y also increases as well. So if I put 2 in for x, we're going to be estimating a little bit here. If I put 2 in for x, 2 times 0.5 is 1, e to the power of 1 is e, which is that 2.71828, etc., etc., and then e times 3 is approximately 3e, or as a decimal, about 8.15 approximately. So somewhere up here, we'll call this 8.15. I know I should be labeling 4, 5, 6, 7, 8, a little over 8, right? So it's going to keep going up and up. What's happened before there? Let's say we have negative 2, right? So negative 2 times 0.5 is negative 1. E to the negative first is 1 over e. So this case will be just 3 divided by e, which is a little over 1. So it would be negative 2, a little over 1. Looks something like that. There we go. There's your graph. How nice. All right, and here are the two formulas for compounding interest. This one is whenever our interest is compounding continuously, and this is for a set time. You might see often a monthly, where n is 12. So that's so we put 12 in for n. Just so we're clear, I'm assuming we've seen these before, but just so we know what each of these means, P is for principal. Principal means the money you start out with. Okay. A is the amount after time t. R is your rate, and we write our rate as a decimal. Okay, please, if you can percent, change your percent to a decimal. Thank you. N is the number of times compounded. If I can spell compounded. Compounded a year. So if it's monthly, your N will be 12 because it'll be compounding 12 times. If it's daily, there's 365 days in a year, except for leap years, but usually we still say 365. We roll with that. And so on and so forth. Quarterly, that's 4 times a year, so on, etc., etc. So let's do some examples, okay? So let's say that you are investing $10,000. I'm going to try to make the problems I give you, in this case, I'm going to be giving you, I'm going to try to make it somewhat lifelike. So you're investing $10,000. Over the course of many decades, the average rate of return for if you invest in the stock market is about between 9 and 10%. We'll go with 10%, easy to work with, okay? So let's find a few things. Let's find when t is equal to 10. T is equal to 25. And also let's find, I gave you the rate, I gave you the principal. Let's say whenever you are compounding quarterly for this one, and for this one as well, just to be consistent. And then let's do daily and daily. So if let's do quarterly first, okay? So Q for both of these, okay? So if I put all my information in, okay? 10,000 my P. My N value is 4. My rate is 0.1. My N is 4 because it's quarterly. T times is going to depend on whether it's 10 or 25. We're going to do 10 first, okay? So you put that all in your formula, and quarterly after time T is 26,850.64. And then daily, we're not doing daily yet. We're going to do time when T is 25. And quarterly for after 25 years is $118,137.16. So, just by looking at quarterly, the purpose of me going through this is the power of compounding interest when you invest, right? Giving it, being patient, waiting it out is very important, and it's why they always tell you, and I'll be saying this in class as well, to start investing early as soon as you get your first job out of college. If you do choose to go to college, and first job you get, you should be investing, and because that way you're going to build wealth and hopefully retire sooner at a reasonable age, right? So that's quarterly. Let's do daily. Daily would be when N is 365. You're not going to see a huge increase from these numbers right here and right here, but you'll see a little bit of a change. So for daily down here, we did get a little bit of a change. So $27,179.10. So we did get a little bit more money, which we expected. I didn't think it'd be quite this much, but it did. How about that? And then for the other one, for when T is 25, and daily for at year 25, you'll get $121,783.23. All right, so a little increase from there too, which is what we expected. Because what this means is when it's compounding daily, what's happening is a portion of your rate, in this case it was 10%, is being compounded each day, which means you're earning interest on your interest more often. So that's why you're getting a little bit of increase the more times you're compounding throughout the year. So that's why as n is increasing, you're going to keep getting a slight increase with what your result will be. Okay. I appreciate you watching, and we'll see you in class. Bye-bye.